Hi guys, welcome back. So in this video, I'm going to talk about process injection. What is process injection? What is the standard algorithm to perform process injection? And in case of process injection, in this video, we are specifically going to look into how we can inject our shell code into some other process memory. Okay, so just few days back, I wrote this post where I was talking about the fundamentals of process injection and what are the steps involved. So essentially, I have just laid down the basic algorithm. How does a process injection works, and what are the relevant functions, and what is the sequence of functions that is supposed to be called. Okay. To hard code this same concept, I have created this mind map, and this indeed depicts the algorithm that we are going to utilize to perform process injection. So just to give you a high level overview of what process injection is, as the name suggests, we are going to inject our malicious code and get it executed inside some other process's memory. So that is what it is. And now let's take a look into the basic algorithm. To perform process injection, we need to know the target process ID, the process in which we want to inject. So in Windows, we have a unique identifier for each process. So that is the PID, process ID. So we need to get that process ID. Once we get that process ID, we need to get a handle to the target process. So all of these steps are in a specific chronological order, and the output from step 1 acts as an input for step 2. So that is why this chronology is important. Once we get the target process ID, we need to get a handle to the target process, and we generally do it using open process function. Once we get the handle to the target process using open process function, we are going to allocate some memory inside that target process, and this can be done using virtual alloc x. Once we have allocated some memory inside the target process, we are going to write our malicious code inside that allocated memory. So what we are doing here is we are writing our shell code inside the target memory. This can be done using write process memory function. Once we have written our shell code in the target process, we are going to execute that code. So execution of the shell code is going to take place using create remote thread function. On the right hand side, you can see the functions that are going to be involved. For now, I'm going to write a little bit of quick and dirty code, and there are going to be definitely options that you can add on to this sort of a code. Here are certain optional add-ons. So with passage of time, I'm going to take a look into these optional add-ons as well, how these things can be added on inside our code to make it more neat, more tidy, and more effective and more modular, basically. To start with the first thing, to get a target process ID, this can be done in multiple ways. We can try to identify the process ID manually by using a process hacker or a process monitor like tool. Or what we can do is we can find the process ID with our code as well. We can take a snapshot of current running process, and then we can iterate through the running process snapshot, and we can try to find the process ID using a name or using some sort of an identifier. For this demonstration, I'm going to take a look into the manual way out. Okay, the easiest way out, I would say. And we are going to manually provide the process ID to our code. So we are going to tell where we need to inject. All right, so let's dive right into the code then. What do I have here? I have a Visual Studio up and running. I have created a blank project, an empty project. I have not created any file so far. So I'm going to quickly create a file in my source file section. Let's create a new item. So I'll start writing the code and I'll explain you as I write the code. All right, so let's start with, as usual, hash include windows.h Let me see how I can increase the font size here. All right, so this looks better. So I'm including the windows.h header file, and I'll just quickly write my main function. And I'm going to pass some command line argument. So I'll go for argc, argv, all right. Before I proceed ahead, let's take few moments to understand what I have written so far. So what is windows.h? Windows.h is essentially the header file. You can say it's like a wrapper that contains the most commonly used header. So it contains the definition of all the functions that we are going to utilize. So that's why I have included windows.h. Later on, we are going to take a look into the documentation. So this thing is going to be clarified later on as well. I've created a main function, and then I have passed argc and argv. This is nothing other than your argument count. So argc is your argument count. What kind of argument? The command line argument that we are going to pass while we are running it. So that is the count. And argv is your argument vector. Essentially, it's an array of pointers to the array of characters. Let's say I'm going to run this program. Let's say my executable is p inject.exe, and then I pass something to this program. Let's say some string abc, and let's say xyz. So my argument count is going to be 3. argc is going to be 3. This is my first, second, and third argument. Okay, so this array is going to contain, so the first value is going to be a pointer to this first argument, and the second value is going to be a pointer to the second argument, and the third value is going to be a pointer to the third argument, so on and so forth. So that this depends upon the number of arguments. Okay, so if I'm going to refer to index number 0, essentially I'm referring to this, the name of the program that I'm running, and index number 1 is going to correspond to the first argument that is passed to it. Okay, all right. So a certain amount of C programming language understanding is a prerequisite. It is a must to understand the code that we are going to write ahead. I would not be able to elaborate each and everything with much details here now. All right. So what I have done is I have created a shell code using Kali. So the code that we are going to inject, write shellcode in the memory. So the shellcode that we are going to inject, I have created it using msf venom. This was the command that I utilized, msf venom -p windows x64 exec calc. So it's a standard calc pop payload, and I already have this payload with me here. So I'll just quickly go to my desktop and bring it in. So I'll just copy this and paste it here. So this is the shellcode that I am planning to inject. Now let's proceed ahead with our standard algorithm. So we need to get a handle to the target process. For that, we need the process ID. So let's just quickly print the process ID here. Let's do printf, and let's do say the target process ID is %i argv1. The first argument that we are going to pass is going to be the process ID. So we do need to typecast it into an integer. So I'm going to use a to I function. So a to I function is essentially used to perform typecasting from strings to the integers. Okay, so that's what I have done here. All right. So this is going to print the process ID on the screen. All right. So now I have the process ID of the target process. So let's get a handle to the target process. For this, I'm going to utilize open process function. Let's just quickly search open process Windows API. So Windows provide very extensive documentation to all its API, and you do not need to memorize any of this thing. All of this thing can be very easily referred to whenever required on the time to time basis. So I'll just give you a brief overview of what this is, how to read Windows API, basically. What can we understand from this structure that is provided to us? This is the return data type, and these values are the arguments or the parameters that are going to be passed to this function. So I can see that here are 3 parameters that needs to be passed to this function. Okay, and these are the data types. Let me just beautify it a little for your better understanding. This is the return data type. These are the parameters that needs to be passed to this function. Okay, this is the data type of these parameters, and these are the attributes. Let's talk a little bit about the data types and the attributes. You do not need to worry about these data types. What Windows has done is Windows has, you can say, created these custom data types for its Windows API. Essentially, everything boils down to the primitive C data types. These data types are nothing but, you can say, type def inside the Windows API. Just for example, let's take an example of D word. So we can see that it's a type def, you can see, and it is nothing but a 32-bit unsigned integer. Okay, so similarly, whenever you come across any sort of data type here, you can refer to this Windows data type documentation, and you can understand what is the data type. Okay, all right, and what is a handle? So I'm not going to take a very deep dive into the handles. Handle, as the name suggests, it's a way by which you can interact with the target process. So you can just derive the meaning from the normal common English word. So using a handle, you can operate an object, you can pick an object, you can control an object. So similarly, in Windows, a handle is a way of controlling a process or an object inside the Windows memory. And with respect to the attributes, so I have this documentation, and here you can see all on the left hand side, you can see all the different kinds of attributes. Okay, so out is just an example attribute. We do not see any out attribute here, but we'll come across out attribute very soon. So out attribute is nothing but something which is going to be returned by the called procedure to the calling procedure. So essentially what is going to happen here is, let's say you pass an argument and the attribute that is set to that parameter is out. So let's say it's a pointer. So by the time this function is going to end its operation, that parameter is going to be modified. Okay, that parameter is going to be updated. The value is going to be updated. Similarly, we do have in attribute here. So let's just quickly find, where is it? Here it is, in. You can see the in attribute indicates that a parameter is to be passed from the calling procedure to the called procedure. I'm just giving you an overview how to read this Windows API documentation. Okay. All right. So let's implement the open process. So I'm going to call open process, and open process is going to return a handle. So I'm going to create a variable named as, let's say, h process. The data type of this variable is handle. This is the name of the variable where I am storing the handle to the target process. And in here, I need to pass 3 arguments. So let's take a look into the arguments. So the first one is DW desired access. Then we have got B inherit handle, and then we have got DW process ID. All right. So the process ID is pretty understandable now. The DW process ID is going to be the PID that we are going to be passing. Let's just mention it here. This is our process ID that we are passing. So let's paste it here. All right. Then we have got DW desired access. So we need to mention that what kind of access do we need on the target process. To know what kind of process rights are available to us, we do have this process access rights documentation. So we can see delete, read control, synchronize, write tag, write owner. Okay. The following table lists the process specific access rights, and these are the standard access rights. Okay, process all access, process create process. What level of privileges do I need on the process object? So we'll take process all access as the first parameter, process underscore all underscore access. So process all access. Now let's try to understand the second argument, that is B inherit handle. If this value is true, process created by this process will inherit inherit the handle. Otherwise, the process will not inherit this handle. So what happens is that this is here the concept of child processes and parent processes comes into picture. So if this value is set true, that means that the child process would have the capabilities to inherit from the parent process. Okay, but we do not need to implement this functionality. We do not need to provide this capabilities to the child process. We do not need it even. So we'll make it as false. So the second parameter has been set as false, and we have already set the third parameter. So our first function call is now ready, open process, and we would be able to open the process, get a handle to the target process. All right. Now, what do we need to do next? We need to allocate memory into the target process. So for this, we need virtual alloc x. So let's take a look into the official documentation. And this is the syntax. All right. So LP void is the data type of what it is going to return. It is going to reserve, commit, or changes the state of region of memory within virtual address space. All right, so that is why we are using virtual alloc x. It is going to take 1, 2, 3, 4, 5 parameters as the input. One of them is optional. Let's try to understand what does these parameters mean. So virtual alloc x, let's try to implement this thing, virtual alloc x. That's what we are going to make a call to. And the first parameter that it takes is the type of handle, h process. So it is the handle to the target process. So allocating memory, we are allocating memory inside the target process. And to allocate the memory, we need the handle to the target process. So from the previous step, we have the handle to the target process. So that is what we are going to pass here as the first argument. So let's pass it as the first argument, h process. All right. The next is LP address. Let's take a look into this. It is optional. It is not mandatory. desired starting address for the region. So this is going to define if we need to provide any arbitrary address, any desired address where we want to allocate, but that is not the case with us. So we'll make it null. If LP address is null, the function determines where to allocate the region. So we'll allow the virtual alloc x function to determine wherever it can find the available memory, it can allocate it. We do not want to provide a specific region in the page where we want to allocate the memory. So we'll make it as null. So the second argument is null. Let's move ahead. DW size t. All right, let's take a look. The size of region of memory to allocate in bytes. So if we go back here, we are trying to allocate memory inside the target process for what? To write the shellcode, right? So the amount of memory that is going to be allocated, that should be sufficient, or that should be equal to the size of the shellcode. Okay, so this is what is being referred here. The size of region of memory to allocate. How many bytes do I want to allocate inside the target process? So what I'm going to do is, I already have my shellcode here. Its name is buff. It's an unsigned char array. So I'll use size of function. So it is going to automatically calculate the size of buff variable and going to pass it here as a parameter. Moving ahead, I can see FL allocation type. Yeah, I hope this is the next argument. Yeah, so FL allocation type. Let's go ahead. The type of memory allocation. This parameter must contain one of the following values. So at least one of the values should be there. Okay, it must contain. And the options that we have is mem reset undo, mem reset, mem reserve, mem commit. So what we want to do is, we want to reserve the memory and we want to commit the memory. And I'll quickly explain you what is the meaning of mem reserve and mem commit. When we are going to set mem reserve, it is going to reserve the memory inside the virtual address space. It is only going to reserve that memory in the virtual address space. It is not going to allocate the memory, or it is not going to reserve any physical memory inside your RAM. Okay, when we are going to use mem commit, it is going to actually reserve certain bytes inside the RAM. Okay, so it says to reserve and commit pages in one step, you can call it with mem commit pipe mem reserve. So that's what I want to do. I want to reserve some memory inside virtual address space, and then I want to commit that memory inside my RAM. You do not need to perform both of these actions right away. So this depends upon your use case to use case. I'm doing it right away because I want to access the RAM. I want to write to the RAM right away, and I want to execute on that RAM right away. So that is the reason behind why I want to do it just now. So I'll do mem underscore reserve and pipe mem underscore commit. All right, let's get back. Then we have got last parameter, that is FL protect. Let's get an understanding of this as well. The memory protection for region of page should be allocated. If the pages are being committed, you can specify any one of this. So FL protect decides what kind of memory protection do we need on the allocated memory. It gives certain examples. It says within enclave, FL protect cannot be any of the following values. All right. When allocating dynamic memory for an enclave, FL protect parameter must be page read write or page execute read write. So this is very important for us, and this is a very major indication of process injection for antiviruses and EDRs as well. What we are trying to do is, we are allocating some memory and we want to set the permissions. The permission needs to be in such a way that in future, we have the capabilities to write something on it, and later on we are going to execute it as well. So we need to have execute privileges as well. We are going to read from that, we are going to write to that memory space, and we are going to execute the shellcode that is written into that memory space. For our use case scenario, we are going to utilize page, execute, read, write. This is a very major indicator of process injection. So page underscore execute underscore read write. All right. In later on sessions, we are going to take a look into how we can avoid this kind of memory permissions, and how we can reduce these indicators of process injections when we are going to take a look into the evasion part. So the process injection that we are currently understanding does not caters the need of any defender bypass or EDR bypass as of now. So I'll leave this thing for some later video. All right. I do not like this small x. I'll make it capital. All right. So this is going to return something. Virtual alloc is going to return LP void. What it is going to return, let's take a look. Return value. If the function succeeds, the return value is the base address of the allocated region of page. If the function fails, the return value is null. And we can get the error using get last error function. So in this code, as I told you in the beginning, this is like a very dirty approach to write a code. We are not performing any sort of error handling here. We are not checking anything. A lot of these functions can fail. Whatever functions we are going to utilize here, these functions can fail depending upon situation to situation. Let's say we are trying to get a handle to a process, but we do not have sufficient privileges. So that open process function can fail. It is not going to return you back with a handle. Let's say we are trying to allocate some memory using virtual alloc, but we have ran out of the memory. We do not have sufficient memory. The size that we are trying to allocate, we do not have sufficient memory. So again, that virtual alloc X is going to fail. So this is just an example. And we are not implementing any sort of error checks here. We are assuming that everything is going to work fine, and it is going to be successful in our first go. Okay. All right. So it is going to return me with the pointer, void pointer to the allocated memory. Let's say my shell memory is equal to this, and let's just set the data type as well. As I can set it as void pointer. What was the data type? I can set it as LP void. So let's do it. LP void. LP void. All right. So we have successfully allocated memory at this point, and now we are going to proceed towards writing our shellcode inside the allocated memory. Okay, so we are going to use write process memory function now. So let's go search for write process memory. It is going to take 5 arguments, and it is going to return bool. So it is going to return true or false, essentially. So handle to a process, a handle to the process memory to be modified. So we already have that. LP base address, the handle must have process VM write and process VM operation. So we do have write privileges. So it is saying then when you are trying to write to the target process memory, you need to have write privileges, okay, and privileges to operate on it. LP base address, a pointer to the base address in the specified process to which data is returned. So this is going to be the address of the memory which has been allocated. So whatever has been returned by virtual alloc is going to act as a second parameter here. Then comes your LP buffer, a pointer to the buffer that contains data. It is the pointer to the shell code that we want to write. So here my shell code is going to come. The number of bytes to be written in the specified process. Okay, so here we are going to use size of buffer, and then LP number of bytes written. A pointer to variable that receives the number of bytes transferred into specified process. The parameter is optional. Okay, so this is an optional parameter. Is null, the parameter is ignored. So we'll just ignore it. We are not seeking any confirmation that how many bytes were written. We do not want to verify it for now. So we'll keep it as null. So let's start preparing this function call. Write process memory. Write process memory. And the first argument it takes is the handle. So h process is the handle to the target process. The second argument it takes is the pointer to the memory where we want to write. This is the variable from my previous function call, virtual alloc. All right. The third argument it takes is the LP buffer. So this is the pointer to the shell code, the data that we want to write. In my case, the name is buff. Let's do it, buff. And the next argument is the size of buff. And the last argument, we can keep it null. So that was how many bytes it has written. So the pointer to variable that receives the number of bytes transfer into specified process. So we can make it null. All right. So it is going to return true or false if it succeeds or not. And we do not need to cater about that thing for now. We do not need to worry about that. At this stage, we have successfully written our malicious shell code inside the target process memory. Now, I want to execute that shell code. How will I execute the shell code? I'm going to execute the shell code using create remote thread. So what I'm going to do is I'm going to create a thread. So create remote thread. Create remote thread is a function to create thread that runs in the virtual address space of another process. Okay. It takes 1, 2, 3, 4, 5, 6, 7. It takes 7 parameters. All right. H process, a handle to the process in which the thread is to be created. So we already have that. Let's try to create this function call, make this function call parallelly, create remote thread, create remote thread. The first parameter it takes is the handle to the target process. So that is H process. All right. So this function definition is also present here. With passage of time, once you are very well versed with the Windows API, you can just refer to these definition suggestions here itself. The second one is LP thread attribute, a pointer to security attribute structure that specifies security descriptor, and new thread determines whether child process can inherit the returned handle. The thread gets default security descriptor. So I believe this is the same attribute that we have already taken a look during the open process. LP thread attribute, inherent handle. So the logic is similar here as well. So we will make it null. Then comes your DW stack size, the initial size of stack in bytes. The system rounds this value to the nearest page. If this parameter is 0, the new thread uses the default size for the executable. So we are not very much concerned with the stack size for now. We do not want to instruct the system for allocating a specific stack size. So we'll make it 0 and allow remote thread to do it by itself. So we'll set it as 0. Then comes your LP start address, a pointer to the application defined function of type this. This is the data type to be executed by the thread and representing the starting address of the thread in the remote process. So the function must exit in the remote process. All right. So essentially what I understand here is that I need to have the starting address of the thread in the remote process. So this is going to be the address of the allocated memory. So that is what I need to provide here. So that is my shell memory. Let's provide it here. And just because it is telling me that the data type needs to be this, so I'll try to explicitly mention it here as well, that the data type needs to be LP thread start routine. LP thread start routine. Yes, it is matching LP thread start routine. And then comes your LP parameter, a pointer to variable to be passed to the thread function. So we are not passing any variable. We can mark it as null. And the flag that controls the creation of the thread, the flag values are 0. The thread runs immediately. Yes, we want to run the thread immediately. So we'll set it as 0. Later on in future sessions, we'll see how we are going to utilize this create suspended state. Okay, this is going to be very important when we are going to talk about defense evasions. Okay, so for now, we'll set this flag to 0 because we want to run it immediately. And the parameter will be set to null. So let's set it as null and 0. Then we have got LP thread ID, a pointer to variable that receives the thread identifier. We do not care about the thread identifier. If this parameter is null, the thread identifier is not returned. So we'll just set it as null. So at this point, we have successfully made all the function calls that were required. It is also returning something. If the function succeeds, it returns the value. Return value is a handle to a new thread. So let's just get that handle, and I'll say malicious thread is equals to this. And that's all. That's all that was required to perform process injection. So I believe I have not included the printf stdio.h. I do not, in fact, I do not need this as well. I'll just comment it. And let's save this now. I have set as a solution to be in the release configuration. So let's build our solution then. So let's quickly click on build. Build started, build succeeded. Let me go to my release directory. Let's open up CMD. I need to provide it with a process ID. So let me open up my process hacker. And I was planning to inject in notepad.exe, but I can see cmd.exe is also good. So it is available to us right in the top. The process ID is 2124. So let's try to inject it in 2124. Let's press enter. We can see that we have successfully popped up calci. So our code is working perfectly fine. There were no errors. Just in case if you want to print this thing as well, we can print it, but we do need to include the stdio.h. So let's include stdio.h. Let's save it, build the solution, build succeeded. Let's run it. Process injection 8080 8080. Press enter. So for a fraction of seconds, we were able to see in the command prompt the output that we are injecting into the process 8080. Okay, I hope that this tutorial was a little bit helpful for you all and you learned something new today. In the next session, I'm going to clean up this code. Okay, so this is a very concise code, but I'll try to implement some sort of modularity in this code. I'll try to extend the functionality. I'll try to put in some sort of error handling in this code. Okay, so all right then. So that would be all for this video. Until we meet again.